Okay, welcome back. As you can see, we're going to spend another day on this concept of how derivatives affect the shape of their graph. Probably last night you went home, tried to work on the homework. Very difficult, very frustrating, very confusing, really annoying. So if you did the homework and turned it into the basket, I want you to go get it and take it out. Okay, it is not due today. Don't turn it in today. You've got until tomorrow to get it done. And we'll have a chance to work on it a little bit today and go over some similar problems. We've talked about the first derivative test, the second derivative test. We've talked about graphing, inflection points, concavity. We've covered a lot of information, and putting it all together can be very, very confusing. So what I'd like to do, and if you look at the calendar, you can see that this was always a 2-day lesson. Yesterday was all of the concepts. Really heavy on stuff, a lot of stuff. One of those videos you'll probably go back and watch again and look at again. Remember, you can go to the YouTube channel and watch them as many times as you like. But right now I want to spend some more time talking about how derivatives affect the shape of the graph. Now you should have just been handed out a sheet that looks like this. AP Calculus, Chapter 4, What Derivatives Confirm About Functions and Graphs. Let's just spend a moment and go over this. Now, if the sub hasn't handed this out yet, if the teacher hasn't handed this out yet, then go ahead and pause the video first, hand this out, because I want to go over it and I want to talk about it. There's a lot of information here, a ton of information, all on this one sheet. So go ahead and pause the video. If not, I'm going to go on and kind of go over this and talk about it and point some things out. All right, so here we go. So let's take a look at this. There's a lot going on here, a lot of really important stuff here. So in the first thing, first square here, y equals some f of x. It looks like some sort of polynomial here. It's differentiable everywhere. It's smooth. It's connected. The graph can rise. It can fall. I've got local maxes, local mins. I've got points of inflection where the concavity changes. Sometimes the tangent lines are above the curve. Sometimes the tangent lines are below the curve. With something that looks like this is a little bit different, though. These two are different. And can you spot why they're so different? Here, the first derivative, the tangent lines would always be positive everywhere. If I drew the tangent lines in, they would always be positive. Similarly here, all of the tangent lines would be negative. So this function is increasing throughout its entire domain. This one is increasing to this point and then decreasing and increasing and decreasing and increasing and decreasing. This function increases everywhere. Therefore, the first derivative is always going to be positive. The graph rises from the right to the left. And it might be wavy as well. I suppose there might even be a zero tangent in there, but there's not going to be any negatives. Same thing over here. The first derivatives are always going to be negative. The graph falls from left to right, and it might be wavy. Now let's take a look at these two. The big difference between these two is the concavity. Notice, I start here and I end there. Start here and end there. It's the same thing, starting and ending. Start here and end here. Start here and end here. But they're very different graphs. The big difference here would be the second derivative. The second derivative here would be positive because this is concave up. Same thing here. The second derivative of this one would be positive. It's concave up. There's no waves anywhere in here. There's no inflection points. There's no changes in concavity. This would be concave up everywhere, concave up everywhere. And here the function is rising, here the function is falling, here the function is increasing everywhere, here it's decreasing everywhere. But the second derivatives would always be positive. Here, the second derivatives would always be negative. Concave down. The tangent lines would be above the function would be below the tangent lines. Even though the function's increasing everywhere here and decreasing everywhere there, it doesn't matter. The second derivative would always be negative. It's concave down throughout everywhere. Here, the inflection point, the idea of the concavity changing. If I think about my tangent lines and draw the tangent lines in here and draw a tangent line, tangent line, tangent line, at some point right here, the tangent lines go from being below the function to being above the function. The second derivative is changing from positive to negative or negative to positive, which means a change in the concavity, which means it's an inflection point. Notice all of the tangent lines here are positive. I could have it the other way with all the tangent lines negative, no change in the first derivative, but the second derivative is changing. If I think about just a very simple parabola, one that opens down or one that opens up, and I've got my vertex where the first derivative is going to equal 0, the y prime changes signs. So here, the derivatives are positive, 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 negative, negative, negative. The first derivative is changing from positive to negative. I've got a maximum. Here, the tangent lines are negative, 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 and then positive, positive, positive. That's what these signs mean. This is my function. The tangent lines are negative, the tangent lines are positive. If the first derivative is changing from negative to positive, I've got 0 here, and I've got a minimum. Here, kind of a bigger explanation about what's going on here. My first derivative is equal to 0. The second derivative is less than 0 because everywhere along here, the tangent lines are above the function. The functions are below. There's no change in concavity here. This whole thing is going to be concave down, but which means the second derivative is less than 0. But the first derivative equals 0, which means that I've got a minimum, some sort of local minimum, or it could be a global. Similarly here, the first derivative at that point is equal to 0. But notice all of the derivatives, all of the tangent lines are below the function. The second derivative doesn't change. This is concave up. The second derivative would be positive everywhere, which means that this point right here where the tangent line is equal to 0 is going to be a local minimum. All right, so that's kind of conceptually what's going on. The first derivative test, here it is in a nutshell. The first derivative test for local extreme values. If the first derivative is equal to 0 and the sign of the first derivative changes at c, then it has some sort of local extremum value at c. Well, what type? Well, it depends. F has a local maximum if the first derivative is changing from positive to negative, which would be this point right here. F would have a local minimum if the first derivative is changing from negative to positive. Negatively sloped lines to positively sloped lines. So here I would have a minimum. So that's my first derivative test. The second derivative test is going to tell me about concavity, the shape. Does it look like, which one of these shapes does it look like? The second derivative test for local extremum values, here it is in a nutshell. If the first derivative is equal to 0, then I have a critical value. Something's going on. And if the second derivative is less than 0, then it's going to be a maximum at c. If the first derivative c equals 0, again, I've got some sort of critical value there. If the second derivative is greater than 0, then I've got a minimum at c. Now, what about if the first derivative is 0 and the second derivative is 0? What's going on there? Well, there's no conclusion, or I should say there is an inclusion. There's an inflection point, but it is not a local max or a local min. So, putting all of this together when graphing, a complete graph of a function f, applying the derivative and the derivative tests. First, to determine a complete graph of the function f, we establish its domain and its intercepts, x-intercepts and y-intercepts. And that's old lessons. We should know how to do that pretty quick and easy. It's intervals of continuity. And again, the best thing here might be looking for, are there any discontinuities anywhere, any problem areas? And differentiability. It might be continuous, but might not be differentiable. When would it be non-continuous? Well, things like jump discontinuities and asymptotes and holes in the graph. But it's continuous at cusps and corners, but it's not differentiable at a cusp and a corner. So we have to watch out for that. its points of discontinuity and non-differentiability, and of course its end behavior. What's this function doing as x is increased without bound or decreased without bound? And this is all stuff that we've talked about in previous classes and previous lessons. And then we're going to use the derivative test to do the following. Find the first and the second derivative. Find where the first derivative is positive, where it is negative, and where it is 0. And then confirm where f is increasing, decreasing, and has extreme values. Remember, if the first derivative is positive, it's increasing. First derivative is negative, then it's decreasing. If the first derivative is 0, I've got an extreme value, a critical value there. Next, looking at the second derivative, where is the second derivative positive, negative, and 0, to confirm where it's concave up and concave down, and where the points of inflection are. If the second derivative is positive, then I'm going to have it's going to be concave up. If the second derivative is negative, it's concave down. If the second derivative is 0 and the first derivative is 0, it's an inflection point, but it's not changing. Kind of like right here. That's an inflection point, but it's not a maximum or a minimum. And then finally, compare the information found above with the graph, viewing window or sketch, and resolve any conflicting information. And then we can put it on our calculator and kind of check it out. All right, so I have an activity for us now. What I'd like to do is I'll ask you to stop the video here, and we're going to hand out a worksheet, and I want everybody to get a worksheet. I know this says calculus project, a group project here, but I don't want you to do it in groups. First and second derivative tests, and I want you to fill in the blanks. We're going to answer all these questions by filling in the blanks. And the things you're going to fill in here is the first derivative greater than 0, less than 0, increasing, decreasing, concave up, concave down? Is the second derivative greater than 0, second derivative less than 0? Do I have a maximum, a minimum, positive, linear? Where do I have sign changes and all that good stuff? So I want you to hand this out, and I want you to work on this. And here's how I want you to do it. I want you to spend about 10 to 12 minutes just quietly doing it by yourself. Shut up and don't talk. Just look at it, look at your notes, think about it, and do the best you can with all the answers. And time it. Give yourself a 10 or 20 minutes or so. Don't go longer than that. And then after about 10 or 12 minutes, then I want you to talk about it in groups. Turn to the person next to you, share your answers, go over it, and spend another 8 to 10 minutes comparing your answers and resolving any differences that you might have here. And argue about this. Spend some time arguing about this. If I was there in class, I would not be helping you right now. I would make sure you did this first part quietly by yourself, fill in as much as you can, take the best guess on everything, and then I would give you the next 8 to 10 minutes comparing, talking about it, and if you disagree, that's fine. Write down what you think it is, and fill it all out, and then we're actually going to go over this. So, about 20 minutes, like I said, the first 10 to 12 minutes quietly by yourselves, and then 8 to 10 minutes comparing notes and comparing answers. Timing is very important here. I'm about to end this video, and then the second video also has a timed activity in it, so I want to make sure we don't spend too much time on this. So again, 10 to 12 minutes by yourself, 8 to 10 minutes comparing answers and working on it together, and then play the second video where I will go over this and I will give you all of the answers, and then we have another timed activity. All right, so go ahead and we're going to stop this video now and take that 20 minutes. And guys, I know this is frustrating. I know it's difficult. It's annoying. Do the best you can. Just do the best you can on it.